Okay, so this is now, yes, about different, well, directions in the overall picture of Wittgenstein's philosophy of mathematics. And the starting point for me is that according to Wittgenstein, mathematical propositions are something like rules of grammar that I take to be perhaps the most important one-liner for Wittgenstein, something that in his mature work he stresses again and again. They are, it would appear, conventions of some sort, or at least, well, something determined by conventions. Mathematical propositions don't describe facts, but serve as supposed to supply a framework for a description, as he says at one point, determining the correct use of language, what in a certain area of discourse makes sense and what doesn't. So Wittgenstein's position can, I think, be labeled as a form of conventionalism. Well, conventionalism has come under a lot of attack, various objections to it that I've discussed elsewhere. I'm not going to go into that now. I think they can all be answered. I just want to mention what, well, I think many people regard as the most pressing one, namely that what's true by convention, for example, that 1 meter is 100 centimeters, could easily be changed. That seems to be an idea of conventionality. We could introduce alternative units of measurement. Whereas the truth of mathematics do not seem to be negotiable in that way. So that's the concern one has immediately with conventionalism. The idea that we might have a radically different mathematics seems a bit uncomfortable. Could we really have conventions that make it mathematically correct to say 7 plus 5 equals 13? Now, Wittgenstein is quite willing to bite the bullet. So Wittgenstein goes in and considers radically different mathematical systems, and his response is that they would not be false. They might be less practical. There may be other good reasons for not adopting them, but he holds firm on saying it's certainly possible for us to have somewhat wacky conventions instead of those that we do have. Well, is that a tenable position? Are drastically different rules of arithmetic even conceivable? Wittgenstein offers some sketches of some radically different types of mathematics to show that they are, but I think the upshot of all that is what we learn from Wittgenstein's own attempts to make good the idea that we could have a radically different set of mathematical conventions. The upshot is that we would have to imagine a different form of life to go with. That's, of course, exactly the anthropological dimension that is our topic at this conference. We would possibly have to imagine living in a very different physical environment, one where objects vanish in strange ways. Right? You remember those thought experiments in part 1 of the remarks. Or again, we might have to imagine people acting and responding in very peculiar ways, being very relaxed about discrepancies, for example, very, very cavalier about getting different results at different times. So it is possible, yes, but only if we imagine a different form of life. And that, of course, is a quite a weighty concession, because it means that as a matter of fact, perhaps contingent fact, but as a matter of fact, no such radically different elementary maths is an option for us. For in our world, objects do not vanish in such a way as to make 7 plus 5 equals 12 regularly applicable without getting us into trouble. Nor are we willing to adopt a form of life involving an attitude of indifference to the discrepancies and contradictions such a deviant arithmetic would be likely to engender. Rather, for us, the application of mathematics tends to be part and parcel of an attitude of accurate observation and attention to detail. So given that we want, what we want to use our mathematics for, it seems to me there appears to be no alternative to something very much like our mathematics. So conventionalism, yes, but there may be good reasons why certain types of alternative conventions are not realistic options. So there can, of course, be huge differences in the extent and development of elementary mathematics, as indeed there have been, if one considers different cultures at different times. But those are not quite what's at issue here. Those are differences of varying sophistication in different areas, not downright contradictions. So if we again imagine the arithmetic based on the number system 1, 2, 3 to 10, and then many as an 11th number. Well, I mean, that would be of limited use, but it would not lead to any results we have to reject as in contradiction with our system. 10 plus 3 equals many, and that system is not contradicted by our 10 plus 3 equals 13. So that is not quite the difference that is most worrying. So if the upshot of Wittgenstein's considerations is then that for people with anything like our form of life, a radically different kind of mathematics is not an option, it may appear doubtful whether we should still regard him as a conventionalist. That's, for example, the line Mark Steiner takes, and I'm coming back to his ideas later on. After all, it can be said conventions are characterized by an element of arbitrariness. When it's conventional to act in a certain way, it's not to be justified entirely by the nature of things. Rather, the correctness of the action is due to an agreement to do things in a certain way, an agreement that could have been different. So in Britain, we drive on the left side of the road, and for the color of ripe tomatoes, we use the word red. But it's easy to imagine different conventions to drive on the right and call tomatoes rouge. That will be equally serviceable. So again, question, is what I said still compatible with calling Wittgenstein a conventionalist? I think so, because at this point it may be argued that our mathematics does in fact contain quite a comparable amount of conventional arbitrariness to language. First, there are similar notational differences, as in other parts of language, just as the French have a different word for red. They have different names for numbers or other mathematical terms. Secondly, that we drive on the left is perhaps comparable to the way we write down numbers and sums from left to right, and not from bottom to top or something. And thirdly, there's of course also the classificatory arbitrariness, not just the arbitrariness of the label. So subsuming cochineal under red, but regarding orange as a different color. Well, that's perhaps comparable to our having a number system base 10. And as we found the room for conventional arbitrariness in mathematics restricted by our needs and interests, the same can be said about the conventionality of traffic rules or of language. So a convention that enjoins people to drive on the right side of the road is, I believe, equally serviceable. But instead of agreeing to drive on one side of the road, we should be enjoined to ricochet from one side to the other, is not a practical option. Right? So you can have different conventions here, but there's a limit to what we could possibly have as conventions without traffic chaos being the result. So again, the equivalent of a radically different arithmetical calculus, such as the one that as Wittgenstein suggests in section 38 of part 1. You remember the Venn diagram, which offers a kind of proof that 2 plus 2 plus 2 equals 4, right? The equivalent of that might be color words whose reference oscillates between complementary colors from one day to the next. Right? So what's called red is applied to tomatoes today and to emeralds tomorrow, and green the other way around. Right? Yes, you could have such a system, but it would be pretty daft, just as having a calculus where 2 plus 2 plus 2 equals 4. So I think the upshot is that Wittgenstein was certainly not a radical conventionalist. I think Dunn gets that quite wrong. But it seems appropriate to call him a moderate conventionalist. His conventionalism is limited by what could be called his instrumentalism. That is his emphasis on the applicability of mathematics. Remember this famous passage saying it's essential to mathematics and in science also be used in mufti, right? So in civil clothing, so applied outside mathematics. That he came in his mature philosophy to regard as absolutely essential to mathematics. So for something to be acceptable as a mathematical concept, it must be suitable for people with something like our form of life, our engineering, mercantile and scientific interests in a world like ours, where many objects are reliably countable and measurable. Right, so that's the first section, so what I take Wittgenstein to be. So you have here kind of two elements, I think, in his thinking. There's a kind of moderate conventionalist element, but there is also some empiricist element, so putting stress on the empirical applicability of maths. So there is some sort of compromise going on here. Now, given that this is the kind of way his conventionalism gets moderated, it may be useful then to pay closer attention to those empiricist or instrumentalist elements in Wittgenstein's thinking. And there's one metaphor that springs out and that has received quite some attention in literature, rightly so. He sometimes suggests that mathematical propositions could be seen as originating from empirical propositions which are then at some point hardened into rules. One of these is the famous passage, hardened into rules. And he presents as simple examples the empirical observations: 2 apples added to 2 apples are found to make a total of 4 apples. Again, experience teaches us that 5 strokes can be grouped as 2 and 3, which induces us to accept 2 plus 3 equals 5 as a mathematical truth, as a rule. So that will be the picture. We can imagine a tribe, so developing this a little bit, a tribe of people having mastered counting, a system of natural numbers, but do not as yet have any technique of calculating. Okay? And now we can imagine them in a piecemeal fashion adopting certain arithmetic statements as quasi-grammatical rules. So with 2 plus 3 equals 5 is not such a good example because it's so obvious, you see it at a glance anyway, that there are 5 things. But imagine people that frequently have occasion to put together a dozen of a dozen in their sort of mercantile dealings, so it doesn't bricks or eggs or coconuts or whatever. Right? So they put them in boxes of a dozen, and perhaps they have 12 such boxes together. So again and again they need to know how many are 12 times 12, and so they adopt as a handy rule, from having counted and always got 144, then they give this out as a rule of thumb that then perhaps hardens into a rule. 12 is 144. Or again, suppose a farmer of that tribe wishes to enclose a rectangular area of 100 square feet. Obviously he wants to spend as little time and material as possible on fencing, and he realizes by trial and error that the bigger the difference between the length of the sides, the longer the perimeter and the more costly the fencing. So a field of 2 by 50 would require 104 feet of fencing. 5 by 20 requires only 50. And it's not difficult then to hit on the best solution. A square field takes only 40 feet of fencing. And we can imagine again that, guided by trial and error, this farming community would soon adopt and pass on the rule that of all rectangles with a given area, the square has the least perimeter. And that could become something like a rule of grammar, a convention. Now, from what I picked up, I'm not at all an expert in this, but reading a little bit the history of mathematics, it appears that that was indeed roughly the way the Egyptians and Babylonians acquired the first rudiments of mathematics, not through systematic derivation or proof, but merely empirically by trial and error. Obviously, such empirically found mathematical rules or techniques can be inaccurate. They can even be false. The Babylonian techniques for determining the surface area of a circle amounted to taking pi to be 3. Now, presumably the results would be accurate enough for their practical purposes, but their methods of calculation for the volume of pyramids or truncated cones were apparently quite erroneous even by their own standards of precision. Right? So, sometimes you do better than in other cases. Okay, so this is by way of trying to to flesh out a little bit this hardened into rules idea we find in Wittgenstein. Now, of a tribe using only a few isolated shortcut rules, such as 12 times 12 equals 144, square rectangle, least perimeter, we would, however, hesitate to say that they have proper mathematics. And why? Because we would expect mathematics to be systematic. That's another idea we also find in Wittgenstein. So if it's just the odd bit, it's rudiments of mathematics, but we hesitate to say that this is a culture that has developed in mathematics yet. So something that seems typical for our idea of mathematics is the idea of the system of techniques of calculation. And that, of course, is also an idea that Wittgenstein found essential to mathematics. So you have here on the handout a quotation from the big typescript. Every proposition in mathematics must belong to a calculus of mathematics. So I'd like to put it like this, roughly speaking, two ideas that are in Wittgenstein. Chronologically, so earlier is what I call the calculus view of mathematics, and later he shifts more towards what I would call the grammar view, right? But without ever giving up on the calculus view. So in the end, they're both there in those ideas. The idea that maths is calculation, but maths is also something like grammar. Right? But those are the two big poles, I think, in Wittgenstein's thinking, with one perhaps being more prominent in a given period, but he never gave up on either of them as far as I can see. Okay, so we have to do better then in order to make make good the hardening into rules thing. We have to move from piecemeal bits of mathematical shortcut formulae to something systematic. And here's an example I've come up with. An early system of calculation used in ancient Ethiopia, also known as the Russian peasant multiplication. It works like this. Of the two numbers to be multiplied, the first is progressively halved, and the second progressively doubled in columns written underneath the numbers till the first column reaches 1. Any remainder of having an uneven number is ignored, and then the lines beginning with even numbers are crossed out, and finally the remaining numbers in the right and the doubling column are added up. So you have an example of that on the handout. So calculating 18 times 33, you get indeed by this curious method for 594. Okay, suppose we have a tribe, well, that was apparently, Ethiopians did it like that, calculating like that. Now, I think the practitioners of this early multiplication calculus would probably not have been able, at least not all of them, to give any mathematical demonstration of why this procedure could be relied upon. In fact, its efficacy was probably widely regarded as magical. For one of the reason I found in the literature as traditionally given for the step of crossing out the lines beginning with an even number was the belief that even numbers are unlucky. So you have to cross them out. So I think the practitioners, the simple folks, they would be taught this, but they wouldn't really know why it worked. So for them it was, it just worked, right? So that's exactly what we want, so not a proof, but a handy method that you can check by trial and error. Perhaps somebody hit upon it when drunk, or I don't know, and it worked, right? Okay, so this would now be something that I think fits the bill. So for the empiricist account here, the empiricist conventional account, I think appears quite accurate. The halving doubling multiplication technique cannot on its own be regarded as providing proofs. Contrary to our ordinary long multiplications, which I think can be fairly easy to be seen to make it clear what, not only that, but why this must be the result. But here it's far from obvious why this works. So we can assume or imagine that it was not established for proof, but by trial and error. And then it hardened into a rule. It was given a quasi conventional status. So we could say what Wittgenstein says in the lectures on the handout, and this rule then becomes a standard of measurement. The rule doesn't express an empirical connection, but we make it because there is an empirical connection. Right? It's important that it works. Right? You can't just take any wacky procedure. It has to be successfully applicable. And that, of course, takes care, it appears, of one worry that Mark Steiner was particularly concerned about, namely the successful applicability of maths. And that can now be seen as something like an induction. Right? So we get it from experience, so it's a small wonder it works for experience, right? If it's really like a process of induction. Yeah, coming to Mark Steiner's ideas now. So here's a reading of Wittgenstein emphasizing this point. But I think Severin also has some sympathy for that. I think I read in the 2007 paper and you agree with many of those points. And Steiner argues that there was a silent revolution in Wittgenstein's thinking in 1937, when the hardening observations of empirical regularities became Wittgenstein's key idea. I think, and of course Alois could check this out with this wonderful new software. I think this is probably a bit simplified. I think the picture is not as tidy as that, because you find the idea much earlier. It's already 1934 lectures, for example. But I think Steiner's probably right that in the mid-1930s there was some sort of shift. I think it was a more gradual shift, rather than a revolution. A shift from a more pure a priori account to one that paid more attention to the empirical underpinnings of successful mathematical calculus. And then Steiner rightly observes that this view is in tension with some middle period Wittgenstein ideas, namely, in particular, the idea of the autonomy of grammar. Especially claims you find in Wittgenstein that grammar cannot be justified by reference to reality. Well, but that's exactly what one does, right? When pointing out the empirical regularities that made it reasonable to adopt the rule in question. It's certainly a justification by reference to reality, and Wittgenstein's use of the word arbitrary would certainly look very misleading. I mean, okay, not true or false, yes, that can be defended, but certainly not arbitrary. It's not adopting the rule 12 times 12 is 144 is not arbitrary, right? We couldn't have arbitrarily chosen 12 times 12 equals 77, right? That wasn't an option. But Steiner does not restrict his empirical regularity account of mathematics to such carefully limited elementary maths we have been looking at so far. He includes, I really, in order to make this idea of hardening to look plausible, I really cherry-picked bits of maths that fitted. But Steiner has no such qualms. He's quite happy to say about all our, at least basic maths, that the proofs themselves, together with theorems, are drawn from experience. That's on that too. And that, I shall argue, is not entirely plausible. So let's move from that Ethiopian halving, doubling, multiplication to our current techniques of calculation, beginning with addition. Of course, you can develop the rest. Long multiplications are based on the memorized table of short multiplications, and short multiplications can be proved by repeated addition. So addition seems to be a good candidate for to start with. So take, in a Kantian spirit, 7 plus 5 equals 12. Is that based on experience? Well, yes and no. Of course, it can be confirmed, and was perhaps first suggested by experiments with apples or pears. But it's also a necessary a priori truth, is it not? Now, Steiner suggests that its necessity amounts simply to its being stipulated to be correct. So given the status of the rule. That's one attempt at dealing with necessity. Okay, there's one objection to this. It's not conclusive, but one worry is this. You might say, hang on, if what we simply adopt as a rule, we don't call necessary. Right? So bishops move only diagonally in chess. Necessary? That's a rule of chess, nothing necessary. You can change the rules as you see fit. Whereas to say you cannot force mate with only a knight, that's a necessary truth of chess, because it's something that follows logically from the rules. So there we seem to be on safer ground, talking about necessity, which speaks against making the stipulation itself necessary. On the other hand, I think one can perhaps defend oneself against this by saying, but consider another example, a bachelor as an unmarried man. There's no inference in that. That just spells out the meaning of the term bachelor, and yet we don't have any qualms calling that a necessary truth. So perhaps what one could say is, the stipulation itself was of course not necessary, but once something has been stipulated, it's a trivial necessary truth that it is so. Okay, so perhaps therefore this kind of objection can be answered. I don't think it's particularly conclusive. But be that as it may, what bothers me more is this, that 7 plus 5 equals 12 has not been individually stipulated as a rule. If that one has, certainly other sums haven't. Rather, what happens is we've given normative status to the whole calculus of arithmetic and regard any individual sum as merely derived from the calculus. But it's not piecemeal. It's the whole system that has the status. And then, second point, the calculus, and now we're sort of gradually going where I want you to go, the calculus of addition is simply a development of the logical implications of some basic concepts. In this case, the concept of, well, the series of natural numbers as developed in the practice of transitive counting. To count, so it's really basic concept, counting, that's where it happens. To count means that each step in a series of conventionally fixed symbols, such as 1, 2, 3, from one number to the next indicates one more, right? Or plus 1. So the very idea of counting brings with it the definitions of the natural numbers as, I think I have it on the handout, so 0 plus 1. Okay, that's perhaps a dodgy one, but certainly 1 plus 1 equals 2. 2 plus 1 equals 3. So it's just a one more. It's just something you can derive from the very idea of counting. And this series of definitions of our counting numbers suffices to generate by logical entailment a sum like 7 plus 5 equals 12. So this is, if you like, also a response to Kant. It's not synthetic, I think. It is analytic, roughly in the way indicated on the handout below. Just taking those definitions and substitute using those definitions, you can easily prove that 7 plus 5 equals 12. Leibniz was the first to make that point. Frege took him up on that, saying, hang on, there's something you've smuggled in here, namely the associative property of addition. And that's true. So you need that. However, I think that is also something you can argue plausibly is implied in our very concept of numbers. Because for our idea of a number in sort of ordinary life, again, anthropological perspective, order doesn't matter. Right? So if you want to know how many of them are there, if you have 7 and then you add one more and one more, how many of them are there? It doesn't matter whether you take the 7 and then add 1, or you first add the 2 singles and then add those to the 7. I think that can be argued also to be part of our very concept. Right? It is there, but there is nothing magical here. It is something that flows from the basic concept as we have them and need them for the most humdrum, ordinary, sort of Sesame Street type counting exercises. Okay, then, yes, so that gets us back to the Tractatus, saying mathematics is a logical method. So it is logical reasoning applied to a very peculiar type of concept, developing the implications of what is laid down in the definitions of our concepts. But if that is so, then I think Steiner must be mistaken. A calculation such as 7 plus 5 equals 12 is not derived from empirical observation. And what's more, it does not stand in need of any empirical confirmation, having the same a priori status as a tautology. So we shouldn't look at it that way. I think that this is the wrong model here. Okay. Yes, perhaps I should should abbreviate a little bit and not go through the next. There's a passage from Weismann's notes here on the handout that Wittgenstein makes the point, and that's another point that I think counsels caution about the empiricist model. He says that anyway, what you find by experimenting with putting apples and pears on the table is not quite the same, because that brings in a sort of physical element of apples and pears being the objects that don't vanish, that continue, which is not quite part of the calculus. But perhaps I don't need to go into that any further. Of course, yeah, it's true that under certain circumstances arithmetic may cease to be applicable. Or is this relevant? Perhaps it's not relevant. Actually, I skipped that too. Sorry, I should have rehearsed this, but I think I don't want to go on for too long. So let me just come to one other point here before there's more to come in this section, in the Steiner discussion. The thing is that actually, if you look at what Steiner says, it's not quite what he has in mind, the kind of generalizing from apples and pears experiments. Rather, what he focuses on is that there are relevant experiences we have of people's regular and predictable behavior in carrying out calculations. So it's the idea that people normally get 625 as the result of multiplying 25 by 25. That kind of regularity is Steiner wants to use for his position. Now, again, I'm not convinced. It is true. I'm not convinced that this does the work that he wants it to do. But it's true that Wittgenstein often stresses the importance of behavior regularities as something like a transcendental condition of the applicability of mathematics. We could not have a system of arithmetic if people could not be taught reliably to calculate in the same manner. That's true. But, and I think that's the objection I have at this point to Steiner, clearly the regularity with which suitably trained people work a certain calculus cannot be the empirical data leading to the formation of that very calculus. The behavior regularities of rule following are prerequisite for any calculus. Right? Also one in which 25 times 25 yields 3. Even if that calculus, you still have to rely on people being able to learn a calculus, to do rule following, right? So the regularity required for rule following doesn't tell you which calculus to pick, and therefore it cannot be roped in to justify our calculus. So that is just a more regular, more general prerequisite of any kind of rule following. And therefore I don't think Steiner can use that as a justification for our having the math we do have. Okay, then so much on Steiner. To recapitulate a key idea, as I say, of Wittgenstein's theory of maths is that maths is grammar, but it had to be restricted by the need for mathematics to be applicable by creatures with certain interests in a certain environment. So that's to say, for arithmetic to be viable, for equations to be viable, they can't just be made true by convention. Essentially, they, or to be more precise, their applications have also to be empirically true. Yet now we encounter what seems to be a third source of mathematical truth that you have listed on the handout. Mathematical propositions have to be true according to the rules of calculation or proof, right? A third element in the game. So we have three key ideas here. Truth by convention, empirical truth, and truth according to the rules of calculation. how can those three be fitted? Now, we saw how the first two can be fitted, but how does the third one fit in here? Okay, so the hardening into rules idea fits only, I argued, some unsystematic rudiments of mathematics, doesn't really fit our mathematics. And let me add to that an exegetical point. From an exegetical point of view, it should also be noted that although Wittgenstein occasionally used the picture of observations of regularities being hardened into rules, the thrust of his considerations of a mathematical proof that become more and more important the longer he thinks about mathematics in the 1940s, those considerations go in the opposite direction. The distinctive feature of a proof is that it does not require observations of regularities, that it can convince us of something once and for all, dispensing of the need of empirical confirmation. And Wittgenstein's key idea, of course, is about mathematical proof, that what makes empirical confirmation dispensable is conceptual change. So that thereby hangs the tale. I'm not going into that, but let me just sort of flag this up. There's a lot on mathematical proof in Wittgenstein, and that I think also sits uneasily with Steiner's idea of empiricism here. I have a little, to break the monotony, as it were, again, some little kind of miniatures from the history of mathematics. Let me just say very quickly that so this opposition between those two of the ideas in Wittgenstein, the grammar view and the calculus view, perhaps the main two, you can see historically illustrated. So as I already said, the Babylonians or Egyptians had a mathematics that was fitted very nicely, kind of empirically motivated grammar view, measurements turned into practical rules for the use of engineers and merchants, whereas the calculus view comes into existence with a vengeance in Greek mathematics. So here we have this, the studies of a class of gentlemen scholars, not so much motivated by practical needs, which they left in the care of slaves, right? So they had the leisure to really think a priori, but they were fascinated by the idea of timeless and necessary truth as established by a priori proofs. So now you have the other model being dominant. Okay, I have a few notes. Again, I think I'm going to just mention those. I mentioned in passing of something, still casting around for what Steiner and others who like the hardened into rules idea could come up with. A nice example of that, giving my opponent some ammunition here, is perhaps Newton's development of the calculus, which I think is a pretty good example of a piece of maths being developed in a way that outstripped the mathematical resources of the time. Mathematicians, even first-rate mathematicians like Lagrange or Euler, thought it mathematically dodgy, but it worked. Right? It was exactly what physicists needed to calculate what the kind of change of speed, acceleration, speed at one moment, things that conceptually seemed highly dubious. How can anything even have a speed without time passing? The very idea seems a bit of a kind of contradiction in terms. The whole thing was problematic from the conceptual side, but it was just immensely successful from application side. So I think here's a nice one the empiricist conventionalists could use. And I'm sure that there are other examples of that kind in the history of mathematics. My guess, right, my feeling is that, however, that those are exceptions. Right? You find those cases where empirical factors really play a role in a piece of new mathematics until mathematics catches up with that and can make these things good also on mathematical grounds. But it seems to me, my impression from my sort of cursory reading of the history of mathematics is that you have to look especially for those cases. And anyway, it doesn't seem to fit, as I say, the basis of our mathematics, our school mathematics, arithmetic as learned at school. So, now finally, what picture I want to suggest. It seems to me that there's something right here which needs to be held on to. So empiricist conventionalism along the hardened into rules model doesn't work on the whole. But that does not detract from the plausibility of Wittgenstein's basic idea. The basic idea is that the quasi-grammatical norms of mathematics must be in tune with experience. I think that is right, that is absolutely right. But where the metaphor of hardening empirical propositions goes wrong, it seems to me, is in locating that process of attuning only at the level of propositions, when in fact it occurs already at the level of choosing suitable concepts. So that, in one sentence, is what I would suggest. So yes, there is this empiricist element, but Steiner locates it too late in the day. It's already when the concepts are adopted that the trick has been done. That's where we should look for the impact of our environment on our mathematics. So I argued above that our arithmetic, our ordinary school arithmetic, follows from our practice of transitive counting. And you can imagine alternatives to them. And I have two on the handout. So you can imagine, and this is taking a cue from section 38 of the first part of the remarks, that Wittgenstein suggests something that can be called overlap addition. A concept of addition which leads to sums like one overlap added 1 equals 1. So it's a bit like, you know, what you apply when you want to calculate the length of a bicycle chain. Right? Two pieces always have to overlap in one to hold together. So if you want to have length, you always have to have this kind of overlap addition. Right? So and so that you may find uses for that, but it's quite clear that it's not quite so useful a concept of addition as ours, because it hasn't got the direct link with our concept of a number of things on the table. Right? So you can apply this, and you can have a different kind of arithmetic, but there is a reason why we didn't, why we have another concept of addition. That's when the kind of conventionalism kicks in, not later. Again, another example. As I said, counting is the anthropologically important bit when mathematics starts. Right? So we could also imagine a tribe with a different counting practice. Right? Suppose they counted 1, 2, 3, and 4, 5, 6, and 7, 8, 9, and there's, after 3 number words, they put in an and. Then what you get, again, what you can derive from that are somewhat strange looking sums. So again, listed here. So 2 plus 1 is 3, all right, but once you have 2 plus 4, you get 6, because there are the ands in there, which you just say out, but and correlate with objects to be counted, but they do not increase the result. So you get a different kind of calculus there. Again, it's a matter of different concepts, right, from which different calculus follows. So, winding up then, I'd say it's misleading to say, as for example Stuart Shanker says, that mathematical propositions are rules of grammar which we freely construct. No, we don't. Free construction happens in a sense of free construction, restricted by considerations of practicality, but free in the sense that it's not true or false. Free construction happens, but on the level of concepts, not on the level of propositions. And once we have our concepts, our mathematical propositions are not freely constructed, but they are derived. So that is the model that I would suggest. So finding room for conventionality guided by experience, but locating that at the level of concept, because that's the only way you find room for the other important ingredient, namely proof. That you derive a logical method. You derive from the concepts you have, the propositions you have. Right? So there you better not do a dumb-it, to put it crudely, and decide piecemeal, oh, I like this one. No, you don't take that one. No, I mean, that's not the way we operate or could operate. There must be some regular rule following, but that must be anchored in concepts. Yes, perhaps, I don't know, kind of a little note at the end, just as a flourish perhaps, something I found in Marx's Sautoir on the creativity of mathematics. So the upshot is that once the concepts are there, right, you really prove, you derive, you do not create in the sense of making things up. Oh, here's a nice proposition, I like that, I create this now. No, it doesn't work like that. It is really within a system of proving, deriving things according to certain rules. But I think, as Sautoir says quite rightly, doesn't mean that there is not room for creativity, because the problem with deriving is that you can derive any number of things, and most of them are banal and without interest, and where the creativity of the research mathematician sets in is to have a feel for what kind of things to derive at what point and to put together with what. But I think I've spoken long enough now to shut up. Thank you.